So we can then write down the formula using the earlier slide for the probability density function of ST. And what you should see is that more or less, if notice that again we're trying to shortcut the formula a little bit, and we're using M for that expression for our drift term, the alpha minus delta minus a half, just to make this formula up here a little more readable. And so what we're saying is that the log normal distribution for ST, if we just look at it quickly, it looks the same as if we just substituted ST for Y in the earlier formula, with one small difference, and that is up here, notice that I don't have just log of ST. What I have really is the log of ST minus the log of S0. And so this is just a more economical way of writing it, namely that the mean of ST involves the log of S and the M term. So when I subtract the mean, which is what we saw in the log normal formula for Y, I also have to subtract the log of S0 and then subtract the MT term. So this is just an economical way of writing it, and it's a standard way. Again, M is just shorthand for that more complicated earlier expression, and this is what you will see in various contexts for the probability density function of stock prices at time t, and namely it looks just like the log normal distribution, has the S out here and has the S inside, but we have to divide ST by S0. Now, with this probability density function, we can define a conditional probability density function. And to do that, we have to recall how conditional probability density functions are defined. You may recall that, imagine, if you will, graphically, that I have some probability density function. And it has a given probability density, let's call it f of x. And what I'd like to do is convert that to a probability density function only for x is bigger than x0. So I'm taking a full distribution, and I want to convert it to what would be called the conditional. What is the conditional distribution of x's? Conditional on the fact that they're bigger than x0. And what you see here is that conditional, and this should again be familiar from your probability theory, a conditional probability function is simply the original probability function. However, I have to scale it, because if I only use the original probability function in my little graph here from x0 to infinity, it doesn't add up to 1. So what I have to do is I have to divide f of x, so the conditional is going to be f of x divided by the integral of f of x from x0 to infinity. If I don't scale the original probability function, it won't have the right probability on the interval I'm looking at. And that's all we're doing here. So if I want the conditional probability function of S, conditional on it being smaller than k, I take the original probability function and I have to divide that by the probability that S is less than k. Well, we have a formula for that from an earlier slide. It involved that n of minus d2. So you'll see here that the probability density that is developed is exactly the probability density we saw a minute ago for G, for ST, and we called it G. And then we're dividing by the probability that S is less than K. Notice there's a hat on the D2 because we're in the alpha model. Same argument for ST bigger than K. What's the conditional distribution of S stock prices conditional on stock prices being bigger than K? Same idea, it's nothing more than the original probability density, but we have to divide by the probability of the condition. That's how we get a total probability mass of 1. And we see again, we have exactly the same G of S formula, but now we're dividing by the probability that S is bigger than K using the N of D2 value that we calculate. So we now have conditional probability functions, conditional on them being bigger than K or smaller than K, in the real world, because we're using alpha. Now, if I wanted to know what are these values in the risk-neutral world, it's easy. I take these formulas, convert alpha to R in both the M formulas as well as in the D2 formulas. And then I get the Black-Scholes D2s. So we can now calculate conditional means. What's the expected value of S given that S is less than K? So if I look at all the distribution of S prices below K, what's the expected value? What's the average value? And so what I have to do is integrate ST. I have to integrate, well, how do you calculate an expected value? You multiply S times the probability density, and you integrate it over the domain. Well, we have a conditional probability function, which is only defined for S less than K. That's our domain. So we're going to integrate our conditional probability function times S. Now, this is a straightforward but admittedly tedious integral. You can use the G functions that we just derived in the prior slide, and it basically requires some substitutions in the integral, completing the square, some of the typical mathematical calculations, and it's not derived in detail in the book. If you like integral calculus, you can certainly try to derive it. It is not it's not too difficult. It's just you have to be careful. And what you find is that the expected value of S when S is less than K is this formula. And you may recall this coefficient, this is the expected value of S without condition. We derived that formula in an earlier slide. So what we're saying is that the conditional mean, conditional that S is less than K, is equal to the mean of S, the original mean, times a ratio of two normal values. And D1 and D2 are defined just as they are in Black-Scholes, but we're using alpha instead of R. Similarly, the expected value of S, conditional on S being bigger than K, is again the original mean of the S distribution multiplied by a different ratio of N of D values. Now, interestingly, the conditional mean when that S is less than K, that's obviously important for puts. And what we see here are both probabilities one sees in the Black-Scholes put formula, N of minus D1, N of minus D2. Again, without the hats, but that's just alpha to R exchange. Notice that the formula for the conditional mean, given that S is bigger than K, well, that's important for calls. And we see both normal values observed in the Black-Scholes call formula. And we're now going to see how these two formulas will, in fact, give us the Black-Scholes formula in the next slide.